Alright, Assalamualaikum. Uh, this is the second part of the topic number 1, which is on the introduction of concrete design. So this lesson will align with the course and program outcome CO1 PO2, which is you need to analyze the reinforced concrete structure according to standards. So at the end, you should be able to describe and explain the limit state design, whether it is ultimate limit state or serviceability limit state. And then you discuss the concept of partial factor of safety in design, and also you need to elaborate a type of loading subjected to structure. Okay, so let's look into the material properties. This is an example of stress strain curve of a concrete. At first, when you apply load, the concrete will react as elastic. The stress and strain is in linear state until it reaches the yield point. Then the concrete becomes plastic. For steel, the stress strain, basically it has the same value, which is the stress over strain in tension and also in compression, where the modulus of elasticity of steel is equals to 200 kilonewton per millimeter squared. Okay, so for material properties, the characteristic strength for concrete, the value of strength of concrete is denoted as FCK. So here is FCK. Okay, for example, let's say we have concrete class 25/30. It means that the characteristic cylinder crushing strength of 25 and the cube strength is 30. However, for design, we take the cylinder crushing strength. It means that for design, we are going to use FCK equals to 25 for concrete class 25/30. Okay, for steel, the strength of reinforcement, since we are using high yield steel, the yield strength of the reinforcement we denote as FYK, and the value is constant 500 Newton per millimeter squared. Okay, so this is the two value that we are going to use later on in our design. Okay, alright, so next is on the limit state. So what is the limit state? Limit state is the condition with the structure or structure element is no longer acceptable for use. Limit state is normally the maximum value. For example, let's say we are going to apply a loading on structure. So how much is the maximum load that we can apply? So that is the limit state. In RC design, we have two types of limit state, which is the ultimate limit state and also serviceability limit states. So what is ultimate limit state? At ultimate limit state, the structure must be able to withstand with an adequate factor of safety against, the first one is collapse. Even at the ultimate limit state, the structure should not be collapsed and or buckling or overturning, and also internal explosion. So it means even though we are designing the structure at ultimate limit state, it must be able to withstand collapse, buckling, overturning or explosion. So what happened at serviceability limit state? In terms of deflection, the structure should be the comfort of the building users be adversely affected. It's not affect the users. And then the cracking must not affect the appearance of the structure, and also the durability of the structure depending on the exposure. Okay, so this is the two type of limit state that we are going to look in RC design. So basically for ultimate limit state, it is on the design or the strength of the structure, but for the serviceability limit state, more towards the appearance of the structure. Okay. For each limit state, they have factor of safety, which is the allowance of possible variation, such as constructional tolerance. So the factor of safety is applied to the strength of the material, the FCK and FYK just now, and also applied to the loading on the structure. Action is the loading on structure. Okay, partial factor of safety for material. To calculate the design strength of the materials, we calculate as the characteristic strength divided by partial factor of safety. Okay, so let's say if we have a concrete, so it means the characteristic strength is FCK, and it must be divided by partial factor of safety for concrete. So this one is 1.5. Okay, so for concrete, to cater for errors during construction. So why do we need to include a partial factor of safety? The first one is to cater errors during construction or manufacturing process. But for steel, we manufactured the steel in stringent care. That's why the partial factor of safety for steel is smaller as compared to the concrete. So partial factor of safety for steel is equals to, this one is equals to 1.15. Okay, so let's say you are going to calculate design strength for steel, so that it means that here is FYK divided by 1.15. For concrete, since we constructed on site, so lead to the human error, so we need a higher value of partial factor of safety. Okay, so the next one is partial factor of safety for loads, the loading on the structure. The load combination is for ultimate limit state, we have permanent load and also variable load. Design load at ultimate limit state is equals to 1.35 GK. GK is permanent load plus 1.5 QK. QK is the variable load or imposed load or life load. Okay, so this is a ultimate design load, and for serviceability limit state, the factor of safety is 1 GK plus 1 QK. So the value of 1.35 is the factor of safety for permanent load, and 1.5 is the factor of safety for variable load. Okay. So to calculate the design load, so basically the characteristic load must be multiplied with partial factor of safety. So why do we need to multiply with FOS? The first one is to cater for errors or inaccuracy due to design assumption. So in design, so basically we make a lot of assumption and also some inaccuracy in the calculation, and also due to possible unusual load increment. So let's say when we design, we stated that the room can be catered by 10 people, but at the end 20 people is coming into the room, so the unusual load increment. So that's why we add partial factor of safety to cater for load increment. And also unforeseen stress distribution, and also for constructional errors. Okay, so action and load. So we have, just now we have permanent action and also variable action. So permanent action, we denote as GK. It means that the weight of the structure, so which is permanent, cannot be moved. Okay, so the weight of all elements in construction, and the constant magnitude and fixed location. So that are the permanent action. For example, let's say if you design for beam, so it means the self weight of the beam. So let's say you design for slab, it means the self weight of the slab. Okay, variable action, we denote as QK. It is the transient and not constant in magnitude. Okay, so variable action is actually the load produced by use or occupancy of the structure. So depending on the purpose of the structure, so what is the variable loads? For example, let's say if you are designing a house, in a house there will be a living room, bedroom, kitchen. So all these area have different variable action. So depending on the intended use. So this one you need to refer to Eurocode number 1. So action on structure. And okay, so the value should not be minimum by the given code, Eurocode 1. So you need to provide your own justification on how much is the variable action on structure. Okay, so loading. So let's calculate loading. The figure shows a simply supported main beam of 5 meters span. So let's say this is a beam 5 meters long. Total unfactored permanent action on the beam is 8.5 kN per meter, including self-weight and brick wall. And unfactored variable action is 1.5. So calculate the design load. Okay, so how do we calculate? So the first one here, it mentions is unfactored permanent action and also unfactored variable action. So what is unfactored? Just now for uniformly distributed load at ultimate limit state, we have a factor of safety. Unfactored, it means that the value given here is not multiplied by the factor of safety yet. Okay, so you need to multiply the loading given here with factor of safety. Okay, so for design load, basically you will calculate for ultimate limit state. Okay, so what is the equation for design load at ultimate limit state? If you still remember. Okay, so it is 1.35 GK plus 1.5 QK. Okay, so this is the equation to calculate design load at ultimate limit state. So 1.35 is the factor of safety for permanent load, GK, and 1.5 is the factor of safety for variable load, QK. Okay, so you substitute, and another one here, it mentions that the value of 8.56 kN per meter is including self-weight and brick wall. It means that this value include the value of the beam self-weight and also the value of brick wall. So you don't need to calculate separate value for self-weight and brick wall. Okay, so you just substitute the equation into the equation. GK equals to 8.56 and QK equals to 1.5. Okay, so we calculate the design load. W is equals to 1.35 GK plus 1.5 QK. And you substitute into the equation and you get your design load at ultimate limit state equals to 13.806 kilonewton meter. Okay, so I think you get until here. Okay, let's move on. So let's say if the self-weight is not included, so excluded. So how do you calculate the self-weight of the beam? So here, permanent action calculation, which is the GK, so all the beam self-weight, flap self-weight and so on is a permanent action, which is we denote as GK value. Okay, to calculate for beam self-weight, the concrete density, you need to times with the width of the beam and the height of the beam. It depends on the size. So the width is the B of the beam times the height of the beam, the cross-sectional area. Okay, so the concrete density is a constant value, which is 25 kilonewton per meter cube. So whatever members that you want to calculate the self-weight, the concrete density always equals to 25 kilonewton meter cube. Okay, so this one is, let's say you are going to design for beam. So let's say you are going to design for slab. So to calculate the slab self-weight, the concrete density times the thickness of the slab times the length of the slab. Okay, so at the end, the unit must be kilonewton per meter cube. Okay, so you need to make sure here the unit since we are going to multiply by kilonewton per meter cube, so it means that the width must be in meter, the height must be in meter. So you need to convert the unit. Okay. Brick wall. For brick walls, we need to know what is the material density. So brick wall, we have so many brick wall materials. For example, you have clay, concrete, and so on. So they have different density. It depends on the materials. Okay. So and then you multiply with thickness of the brick wall, multiply by the height of the brick wall, and make sure the unit is similar. Okay, for plaster, you need to find out what is the load intensity of the plaster. Then you need to multiply with the thickness of the plaster that you are going to use. So all of this is the permanent action GK. Okay, so let's try another example. Example number 2. Here is the same question. It's just that here we denote as 8.56 is excluding self weight and brick wall. It means that it's not include here the self weight load and also the brick wall load. So you need to calculate what is the self weight of the beam. The beam size is given here, 250 mm times 500 mm, and then the brick wall. Given here the brick wall is, this is the density of brick wall 23. The thickness of brick wall is 230 mm. And the height of the brick wall is 2.5 meter. Okay. Alright. So next is how do you calculate the self weight of the beam? Okay. For example number 2. So this is what it looks like. Okay. So the beam, the 5 meter beam has a brick wall on top of it. So the beam will carry the load from the brick wall. So the self weight of the brick wall. So here is the beam size, B times H. Here is the height of the brick wall and the thickness of the brick wall. Okay, so first calculate the self weight of the beam. Okay, concrete density times width times the height of the beam. So given that the concrete density is 25, the beam size is 0.25 times 0.5 because we are converting to meter. Just now the beam size is given as 250 mm times 500 mm. Okay, so we get that the beam self weight is 3.125 kilonewton per meter. Okay, it is permanent load, so we denote as GK. Alright, so next you calculate the brick wall self weight. So brick wall self weight equals to brick wall density given in the equation. Brick wall density equals to 23 times the thickness of the brick wall given at 0.23 mm, and the height of the brick wall is 2.5 meter. So that you get brick wall self weight equals to 13.225 kilonewton per meter. Okay, so now you get the brick wall self weight and beam self weight. Then you need to calculate what is the total permanent action on the beam. Okay, so total permanent action is you need to total sum up all the GK values. So you have GK value given in the equation plus the beam self weight plus brick wall self weight. So then you get the total permanent load. And for variable load given in the equation, the QK value is equals to 1.25. Okay, so in total what you get is the uniformly distributed load is equals to, so you substitute into here 1.35 GK plus 1.5 QK. So GK here is 24.91 and QK is equals to 1.5. Then you get your uniformly distributed load equals to 35.88. Okay, this is your final loading. Okay, so I hope that you can get on how do we calculate the loading, because after this we are going to use this loading to design our members. Okay, alright, so I think that's the end of our lecture. So here is how do we calculate the depth of the beam. So let's say this is the beam width and the beam height. In design, we only consider the effective depth D value, which is the value of from top of the beam to the center of main reinforcement. Okay, so effective depth is given as total height minus cover, here cover, minus the length diameter minus diameter bar divided by 2. So then you get your effective depth value. Okay, so that's all for topic number 1, which is on the introduction. So please fill in the entry survey in the portal. Okay, thank you very much. See you next time.